Boom. You guys all set? All right. So, Lindsay, this is everything you missed. You ready?
Yeah.
All right. Goes like this. So, guys, in review, as a way to catch up with where we are, after having what for me was a fascinating and yet had nothing to do with the class conversation, but every now and then we get to have days like that. Guys, we got to this point. And we talked about this idea of electromagnetic radiation. We talked about the idea that these are waves that travel through vacuums. They all travel the speed of light. And they transfer energy from one place to another. And we talked about radio waves and visible light and gamma rays and everything in between being the same kind of radiant energy. But we then talked about the idea that the only difference between radio waves, be them AM and FM, and guys, did you also know that it's in this band where Wi-Fi and our cell phones work? Did we talk about that? Yeah, guys, this is the range in here sort of between radio and microwave where Wi-Fi and cell phones work. Actually, the 5G stuff that they're doing now is pushing deeper into the microwave band. Anyway, so there you have it. And then infrared, visible light, ultraviolet, all the way across. So, guys, when we then understood about how to talk about these energies, the thing that we talked about to start out was this idea of wavelength, and that all of these things are waves, and therefore there's literally a length between two repeatable points that describes how long these waves are, ranging from radio waves that are on the order of meters to kilometers, all the way down to gamma rays whose wavelength is on the order of the size of the nucleus of an atom. But then, guys, using this slide, we then brought in the idea of frequency. And frequency is how many of these waves cross a point in 1 second. And we said that wavelength and frequency are inversely related. So if we have a long wavelength, we have a relatively low frequency, like 10,000 cycles per second or hertz. If we have a really short wavelength, something like gamma rays, then we've got frequencies that are approaching Avogadro's number, off by about 3 powers of 10. But guys, those are sort of our ranges of values. And we then related this to energy, understanding that these are high energy waves. That's why gamma rays give you cancer. These are low energy waves, and there's radio waves all around us, and we bear that just fine. So guys, that's where we're at. Lindsay, that's what you missed, although it took us 70 minutes to get there. Guys, what do you need to clarify or chat about or dig into gently as we move forward? You guys good on all of that? We okay? All right. So guys, then we turn this into... Mila? I know, but you could laugh. Thank you. Then guys, we turn this into this, and we turn this into math, and we jumped over here, and this is where we got to last time. We lent some numbers and some units to this. Wavelength, which is abbreviated the lowercase Greek letter lambda. I think on the AP equation sheet, they don't put the little sexy cross on there, do they? Can you find it? Because you got to find this on your equation sheet, so let's go get it. I don't think they put the little crossy thing on there. They don't. Where are we at? Oh, atomic structure. Isn't that interesting? Atomic structure and the equations that we have are all about waves. Aha. No, they don't put the sexy thing on there, but that's fine. All right, and then guys, we've got frequency, which is abbreviated the lowercase Greek letter nu. It looks like a V, but it's not. V is velocity. This is nu, which is frequency. Notice the units, guys. That wavelength is measured in units of length, which are for us meters. And then, guys, these are our units for frequency. They are hertz, which are inverse seconds, which are cycles per second. So now when you go to buy a television at Costco and it says it is a 120 hertz television, you now know that that means the television is redrawing the image 120 times a second, because you now know that hertz are seconds. So guys, what do we need to talk about with these ideas? You good? All right, so now this takes us to where we stopped last time and the math that we're about to do. And guys, the math that we're about to do is bringing these units together. So we have wavelength that is in meters. We have frequency, which is in cycles per second. And we found out that magically when we multiply those together, we get units of speed or velocity. We'll use them interchangeably, but we already know the speed because they're all going the speed of light, and that gives us this. The speed of light is equal to the wavelength of the wave times the frequency of the wave, and that gives us speed. Because it's constant. Yeah, literally, it's because it's constant. When Einstein got all uppity and said the speed of light is constant, they abbreviated it C in honor of the idea that it's constant. Yeah, go ahead. It's okay. Because I was going to say something snarky. You're not going to have to worry about it. Yeah, yeah. Because they're unrelated sciences, contextually we understand. You guys good? Okay, solve this. So guys, it says this. Don't write down the question, but figure out the answer. It says the yellow, and can you picture this? Like, you guys know that magically in Orem there's a law that says everywhere there's an elementary school, there has to be a park. You guys know that? Think about it. Your elementary school butted up against a park. And that's not coincidence. No, it's a Utah County law. But guys, that's not true. To my knowledge, anywhere else. Everywhere that there's a school, there's a park. That's not coincidence. But it's also not universal. But guys, the reason that I bring it up is in a lot of these parks, there's typically like space between, but it's space that they like to illuminate just for safety reasons at night. And so you'll see these telephone poles that have these large lights hanging off of them that tend to have these large open at the bottom glass globes. And at night when they light, you can hear them hum, but you also see that the light has a yellow tint to it. Guys, what's going on? Those are actually what are called sodium vapor lamps. And you may remember from the flame test lab that we did last year, when we flame tested copper, it was green. When we flame tested lithium and strontium, it was red. When we did potassium, it was purple. But when we did sodium, it was yellow. Guys, that's what's going on inside there. The bulb from that sodium vapor lamp actually has sodium gas in it. And the electricity is actually exciting those sodium atoms. So this is the question. So these yellow lights give off light with a wavelength of 589 nanometers. What's the frequency? Solve it. So guys, I'm asking you to solve this for two reasons. One, it's going to become the foundation for what we're going to learn today, because this is headed somewhere, and we're going to need this number. The other reason that I'm having you solve this is because the units get tricky. There you go. Yeah, so actually, here, let me just lead you to it. It's 10 to the negative 9th. Yeah, nano is billionth. But guys, you'll notice that we write that in sort of a strange way, that it is a number in the hundreds of nanometers. You're going to find that conveniently all visible light, and again visible light, which we understand there's nothing special about, other than that our eyes can see it. Guys, visible light is always in the range of hundreds of nanometers. Ah! Oh, hey. You should be. Claire, I love that you think like a teacher. Your mind automatically went to, did he buy that with tax dollars? And the answer is, heck yeah, I did. I'm about to shoot you with it. I got to make sure it's sighted in. That's pretty good. I was aiming for the outlet. I know. Well, these are supposed to whistle. They have a little whistle thing. They don't always work. Did you guys get a number? All right, so what I'm going to do is this. I'm going to push the calculation to a blank page so that we can reference it back and have space to refer to it. But guys, work with me through this calculation, because some of you are going to approach this calculation from an angle that makes sense mathematically, but is going to screw you up when you start doing these calculations later in the year, because you're making it more correct than it needs to be. So the equation that we're solving is simply C is equal to lambda nu. And so, guys, in this question, we were given lambda. We were given the wavelength. It's 589. And C is a constant, as John got us thinking. So now we need to know frequency. We need to know nu. And so, guys, I learned 3 times 10 to the 8th meters per second for the speed of light. But what does it give you on the AP equation sheet? It's what? Oh, seriously? Tell me again. 2 point what? 998 times 10 to the 8th. Isn't it? It's 8th, right? Okay. Meters per second. And then, guys, we are given the wavelength. And here's where we've got to be careful, because this is 589 nanometers. But guys, the problem is that we can't use 589 nanometers because the speed of light is not in nanometers. So guys, we've got to figure out how to approach this. Guys, you know you best. You do math like you want to do math. My strong advice to you would be, don't muck around with the speed of light. Don't turn that into nanometers. You're just asking for trouble. So guys, how do we convert this into meters? Well, all we've got to do is add what nano means. Nano is 10 to the negative 9th. Now guys, please don't do this, but I've had students in the past that have been like, I don't like it like that because the decimal is supposed to be here, and they make it 5.89 times 10 to the negative 11th. I would strongly encourage you not to do that, because it's just a place to make a mistake. So guys, leave it like this, and then you've got your X, which is your frequency, and then, oh, and this is meters. And then guys, if you go through the math, the meters cancel, and magically you're left with inverse seconds, which is hertz. All right, I know you guys got the answer, but I just want to have the experience of doing this. So 2.998 times 10 to the 8th divided by 589 times 10 to the negative 9th. And what do we get? 3 digits? 5.09 times 10 to the 14th? Okay. Just 1 second. So 5.09 times 10 to the 14th. But guys, you understand that's not yet correct. What's missing? Units. Now guys, this is up to you. Check this out. You could put hertz if you'd like. Frankly, I don't prefer that because that is a number that I can't then do additional math with. So my preference is to go inverse seconds because that's a number that I can work with. Claire, was that you?
Yeah. So
Yeah.
I manipulated the equation before,
Mm-hmm.
like the number correctly, but
Yeah.
I don't know if I missed something else, but it ended with my units being seconds, but not hertz.
Probably because it's in the, this is weird, it's in the denominator of the numerator, which actually pushes it to the denominator.
Yep. Okay.
Right? That's a sentence I've never said before. The denominator of the numerator. Yeah. All right. So, gang, are we good? We're good? All right. So, guys, we're going to tuck this number in our back pocket for a minute. And we're going to talk about what we're talking about. So, we understand that we can go from frequency to wavelength and wavelength to frequency, yes? All right. So now, guys, probably this is going to freak out, but let's just ride the wave. So here and here. And then, guys, what I want to do is this. Let's first of all check our numbers. You have them in front of you. Let me darken the lights so that we can see color a little better. So guys, first of all, this, what was our frequency? I'm sorry, what was our wavelength? 589 nanometers. So guys, these units are in nanometers. I can't touch my board. Well, here. Now I can touch my board. So here's 500. So here's 550. Here's 575. And we were what? 589? Putting us about here, which is hot in the middle of what color? Yellow, which was the question, right? 589 nanometers is in the yellow band of the spectrum. But then we took that 589 nanometers and we converted it to frequency, and what did we get? I don't remember. So 5 times, about 5, and what was our exponent? 14? Okay, so we're about 5 times 10 to the 14th, and if we look here, here's 10 to the 14th, here's 10 to the 15th, so 5 would place us about in the middle of that, which does in fact place us in the visible band of the spectrum. We don't have enough granularity up here to know that specific wavelength or frequency. I don't think, yeah, it would have been nice if they'd actually labeled this off. We could easily do the math. But we know that our number is at least reasonable because it's in sort of the middle of the 10 to the 14th range. So it does set us in the visible spectrum. You guys good? Okay. So now, guys, this. And this is the interesting transition. Don't miss this. So we just did a bunch of math all about yellow light. But guys, do this backward with me in your head. Light is a form of what? Electromagnetic radiation. And electromagnetic radiation carries or transfers what? Energy, right? So electromagnetic transfers energy, but guys, thinking of specifically visible light, where does it come from? Electron not jumps, but falls. Can you do that in your head? So guys, we're doing math that is talking about electromagnetic radiation, and for now we're going to specifically say visible light. Where does visible light come from? Falling electrons. And then guys, what does this light do? It transfers energy. So guys, what we've got to do now is we've got to snuggle up with a really, really interesting idea. You ready? Well, yeah, let's go. Let's do this first. What about, so this is a jump, but bear with me. Guys, is an electron, new conversation, is an electron a particle or a wave? Both. And can we settle into that? Now what about this? Is light a particle or a wave? It's also both. It's a yes. So guys, this is then where we need to make this transition. Humor me for a minute as I catch up with the slides that we just left. So we just did this, right? Okay, so what we just did is we did the math that treats an electron as if it's a wave. So guys, I'm going to turn the lights back on. And imagine that this light up above you is actually the yellow sodium vapor lamp that we just studied as if the light is a wave. But guys, now we need to think of this light as a different thing. So guys, imagine that you could look up at this light. We'll say it's our sodium light, but it doesn't matter. And guys, we understand that it's transferring energy, right? So anyone in black? Yeah, so Michael is actually experiencing more energy transfer than, for example, Jonah is, because here we've got black, and this absorbs more of the colors of light. This is white, which isn't a color. It means it's reflecting all of this light. And you guys have experienced this when you go out on, you don't want to wear black on a hot day, right? That's the idea. So guys, we're comfortable with the idea that this light is transferring energy. But now we've got to think of that energy differently. We're not going to think of this energy now as a wave. Because guys, if you've ever sat in the ocean, you know that the ocean waves bring energy to you, right? But at some point, it just becomes this constant flow of energy flowing over you. And guys, that's the way we think of waves transferring energy. Now we've got to think of them as particles. And guys, what do we call particles of light? Did you pick it up in the chapter? Photons. So now, guys, we are not going to think of we're not going to think of light. Did you just get a shield? Brilliant. We might need to goggle up. Oh, put on, all right, everybody, PPE. So, guys, this... So we had a teacher here. This was actually in the old building. It was that long ago. And she was a little frisky, this girl. So she had this weird thing. She was an English teacher. And she would hand out papers. Some of you are going to think, wait, you do this to us. But she would hand out papers by just throwing them into the room. Like, all right, guys, here's your homework. I don't know. She thought it was cool. And so for some reason, she was throwing filing cards out to the class. And you can imagine she just took a thing of them and hucked them at the class. And then one of the kids picked it up. And have you ever flicked like playing cards and you can turn them into like a boomerang? He flicked it back at her and it came by and she got a paper cut in her eye. It was a heck of a shot, but yeah, she ended up needing surgery. And hopefully she learned not to do that with students anymore, but that's not the point. Okay, so guys, this then is how we're going to play this game. So guys, the idea is this. So we understand light is a wave, right? Wavelength, frequency, all that good stuff. But guys, when we drew, let me just bring it up on here so we don't have to page back. Guys, when we drew this, right? The picture that we started with today, we also associated it with energy, yes? Yes? Higher energy is which end? The gamma or the radio? Gamma. Lower energy is radio. But guys, as that relates to light, and you learned this last year, what color of light is the lowest energy? Red or violet? Red is low, violet is high. Okay. So guys, now we need to start thinking of this light as a particle that transfers energy. We understand waves transfer energy, but guys, this is where this gets weird. Because if you're picturing light as a wave, then I could stand back here and I could transfer it. It's not even loaded. I love that I have my finger out of the trigger guard, right? Okay, so when we think about light as a wave, can you imagine like Star Trek, old Star Trek, William Shatner, and it just creates this wave that transfers energy, right? Guys, that's actually not the way light transfers energy. It's more like particles called photons. I'm good with this. Remember, I raised a male son. The worst was airsoft. Those are not soft. Oh, yeah. I know. Oh my gosh, right? My son had this airsoft gun, and we set our dog's dish across our backyard, which is about 100 feet across, and we were denting the bottom of his dog dish at 100 feet. What's that? Oh my gosh, it's horrible. Okay, so back to this. All right, so guys, now we're going to let this right now be our yellow light. But you've got to understand this yellow light, like all light, is not like a ray gun. We are actually transferring energy, this is important, in packets. And these packets are called photons. So this is going to be our yellow light. Disregard the fact that these are black, because black is not a color. But if this light is going to transfer energy to Liam's book, guys, it can't just go, it's not like a stream hucking light over there. So guys, what we're going to say is that this is a photon that carries, let's just use an easy number, 1 joule of energy. So this is our sodium vapor light up here, right? And when this sodium vapor light transfers, you have goggles on. When this sodium vapor light, this is why you want to teach chemistry. You could never do this in a math class.
You could.
No, they'd lock you up. Oh yeah, in chemistry you can get away with this. Yeah, it's awesome. Did that hit you? Nice. Okay, so guys, the idea is this. Each one of these darts transfers 1 joule of energy. So let's count. Let me get a couple more. Let's count how many. I'll warn you now. I know, right? Okay. No. All right. So guys, let's count how much energy Liam's book is absorbing. Ready? How much energy? 1 joule. Then here comes another photon. How many total joules? 2. How many now? How many now? And you get the idea, right? So guys, and one more. But you get the idea that, guys, if this sodium vapor light is releasing 1 joule photons, is there any way that Liam could end up with a total energy increase of 3.5 joules? No. 2.9? No. It always has to be a multiple of what? A multiple of 1. And guys, don't miss this, because this is the crazy math that gets us from Bohr to Schrodinger in a minute. Guys, this is what Bohr realized. So guys, don't just let this be more than me just shooting darts, because this is important. The idea is this. Understand that Bohr could not see falling electrons. Bohr could not immediately know where this energy was coming from. But guys, do this. Liam is now Bohr. And Bohr, remember what he did? He studied light, right? So what was Bohr doing with that light? And the answer was he was counting joules hitting a detector. And he's got his yellow light. I'm not going to shoot at you anymore. He's got his yellow light, and he's shooting this yellow light at a detector. And he's counting the amount of energy in joules. And it's 1, and it's 2, and it's 3, using simple numbers, 5, 6, 7, 8, 9, 10. But it was always a multiple of a smaller number like 1. Now, guys, what did Bohr do with that information? Where did that take Bohr's brain? Because, guys, this is bordering on, like, it's brilliant. So, no, we didn't go there. Go ahead, Jared. That's true. And so Bohr made that connection first, that this energy is being released by falling electrons. But what is the significance of the idea that energy is always a multiple of a smaller value? Go ahead.
It's not like gradual thing. There's like certain things that are hitting that gives it increasing boost. It's not like a stream with like certain stuff.
Okay, so yes. And so it's back to the idea that it's not a stream, but it's small amounts of energy. And guys, by the way, we're going to give a name to that. It's called quantized, specific quantities. And so he called it quantized energy. But you're not there yet. If the energy of light is quantized, and if energy comes from falling electrons, what must then be true of those electrons if the energy is quantized? That's it. They can only be in certain places. So guys, this is the idea. Oh, I turned my board off. So guys, this is the idea. This may be worth writing down if you'd like. Wait for my board to turn on. We're going to draw some pictures. Here we go. There's our math. That should work. Oh, it really freaked out. But that's okay. We'll just leave it be. So, guys, this is the idea. So, this is the nucleus of an atom. And imagine that the organization... Oh, I don't like that. Imagine that the organization of the electrons around this nucleus is like a ramp. So where does light come from, y'all? Falling electrons. So if an electron were here and it fell, it would release the energy associated with that fall. But if the energy was here and electron was here, or here, or here, or here, or here, or even here, what you would find out is that an atom would release an infinite number of different photons of energy. If electrons can be anywhere, and if electrons can fall from and to anywhere, then guys, we should see energies being released with an uncountable number of energies. This is what is called... How do you spell continuous? E-O-U-S? Yeah. U-O-U-S, thank you. This is what is called continuous energy. So guys, what kind of atomic model would make this possible? And the answer is the Rutherford model of the atom. And remember, guys, Bohr was, do you guys know this? Bohr was a graduate student of Rutherford's. It was actually Bohr that did the gold foil experiment. Rutherford got credit because he was the professor. But guys, it was actually, this was Rutherford's idea. We had the plum pudding model of the atom. Bohr discovered the nucleus, but didn't know what, I'm sorry, not Bohr discovered, Rutherford discovered the nucleus, but still thought the electrons were the pudding. So when Bohr did this experiment, he figured there would be an uncountable number of energies that were released because these electrons could be in an uncountable number of places. But that's not what he saw. As he was gathering this energy, again, Liam, I won't shoot you, But it was, hey, let's find the energy from this yellow light. And it was 1, 2, 3, 4, 5. Way smaller numbers, but you get the idea, right? But then when he changed colors, do this in your head. Then when he changed to, let's say, violet light, how were his results different? If he switched to violet light, how would his results be different? Chat with the person next to you. That was it. More talking. It's weird, but that's actually wrong. Yeah, let's talk about it. So, guys, let's go, and again, sound bites, right? But I heard Jared say something interesting, which actually is not correct. So, I love that you guys were talking about different amounts of energy. Lindsay and Clara were down in the gamma range. But then this idea came to the surface that said it would be the same fundamental underlying value. In our dart example, the 1. But guys, that's not the case. So the analogy is more like this. Instead of a little Nerf pistol, what we actually need, and I have a whole crate of these down in my I should bring one. What we actually need is one of those big Nerf Gatling guns that runs on batteries with the big old wheel with the and it's like got the Forever magazine, and then it's whap, 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 right? Because violet is higher or lower energy than yellow, higher energy. So when he repeated this with something like violet light, it was bam, 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 more energy, but still the multiple of a single value is just with violet light, that single value would be greater. Because violet light has more energy than yellow light. Does that make sense? But, and guys, this is then the quantum leap, if you will. What did Bohr intuit about the higher energy of violet light? Longer fall. Don't miss that, guys. Longer fall. And so Bohr brought these ideas together, and I would encourage you to scratch this down with me. Bohr brought these ideas together, and he fell upon a model called the quantized. It's not quantitized, it's quantized. Q-U-A-N-T-I-Z-E-D. The quantized model of energy. And guys, Michael said this very well. What does this tell us that energy is quantized? And what it means is that there are places that electrons can be, and there are places that electrons can't be. And hearkening back to a model that we drew last year, energy level 1, energy level 2, energy level 3, energy level 4, and so on. And then guys, remember what we did with this? We broke it down into sublevels. Remember that? That's what we're talking about. So guys, what this now means in the Bohr interpretation of the model is there are places that electrons can be, and there's places that electrons can't be. And from that video that we watched last time, which understandably was weird, when an electron jumps from one of these levels to the next, it doesn't travel through the space in between. And when it falls back down, it also doesn't travel through the space in between. But guys, what is necessary to get it to move up? What kind? Doesn't matter. Could be electricity, could be heat, could be electric, could be other light. Do you guys know that's how these light bulbs work? Can we talk about it for just a second? How do fluorescent light bulbs work? And guys, the answer is it's a two-part emission of energy. Have any of you ever broken a fluorescent light bulb? They're full of powder. That whole tube is glazed into powder. And what happens is there's an electrode at both ends of these tubes, and there's gas in the middle, kind of like the cathode ray tube. But guys, when that current flows through the tube, it actually creates ultraviolet light. But you can't see ultraviolet light. So what happens is that ultraviolet light hits the coating that's on the inside of the glass, and it excites electrons in that coating, and then they re-radiate that energy as visible light. So you're not actually seeing the light of the gas, you're seeing the light of the falling electrons that are in the coating inside the tube. But at any rate, guys, it doesn't matter what kind of energy goes in. When energy comes back out, that energy is re-radiated as light. And so the idea is that in this atom, we could see an energy change there. We could see an energy change represented by this. We could see an energy change represented by that, but nothing in between. Does that make sense? So where then, guys, if all atoms are 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, guys, why do we get all these crazy colors for all these different elements? Yeah. The orbitals have different sizes because of the number of protons. If we were to turn this into a helium atom, then all of these would shift down, but they don't shift down proportionally. The inner ones come closer than the outer ones do, and as a result, we now have different distances and therefore different colors that can be emitted. Do you get the idea? Okay, so guys, this then is the miracle of what Bohr was able to do. But now we need to do the math that Bohr figured out from, well, actually it wasn't Bohr. It was a guy named Max Planck who worked with Bohr. So again, we were shooting darts at Liam, right? And what were we counting? Joules of energy. But then, guys, we also talked about the idea that if I had a bigger gun, more energy, more joules, right? But what we've got to understand is that photons of yellow light, I'm not going to show you, photons of yellow light have an amount of energy, photons of blue light have more energy, and so on, right? So how do we measure that energy? And guys, this is where we're going to wrap up today. This is how we measure those amounts of energy. So you guys tell me, are we okay with this idea of quantized energy? And we call these things photons? Is that okay? All right. So then, guys, this equation. This guy you want to write down. So guys, energy is related to frequency. But we also understand that frequency is related to wavelength, and you can kind of see where the math is headed. But guys, the idea here is that the energy of these photons, these darts that are hitting Liam, guys, those darts are a function of the frequency of the wave. So now we've got particle and wave crashing together, because this is the energy of a photon. But this photon, when it behaves as a wave, has a frequency. But guys, please don't have this idea in your mind that this photon is actually wiggling back and forth like a wave. It's not this. So if this was my photon gun, when I shot Liam with the dart wasn't actually doing this. It's traveling in a straight line. It's a particle. But it's a particle that also behaves as a wave, but those are separate characteristic properties. But they come together in this equation, that the energy of the photon is some way equivalent to the frequency of the associated wave. I'm going to let your physics professors in college sort that out with you. What you need to know is this. H is Planck's constant. Don't write it down. Find it in your notes, in your equation sheet. Did you find it? You guys good? Okay. So guys, this then is what this means working this backwards. In the same way that Liam could only absorb energy in multiples of our photon energy, which was 1, guys, when you're standing underneath this light, this yellow light that we already figured out the frequency for, we can figure out the energy of each one of those photons. Please do that math, and then we're going to wrap up the day. Guys, this is going to be another one of those that when you get to college, you are going to go, I'm so glad I took AP. It's amazing how complicated we can turn this idea of quantized energy into. And certainly, not surprisingly, there's a lot more to it than this. But guys, at the end of the day, you're going to have the foundation to understand this. What's that? You're cold. So guys, let me just do the math with you. All right, so now we've got our next equation that says yes, it's called the joule second. Yeah, so let's do this. So energy is equal to h nu. Energy is equal to, ooh, can somebody give me, well, let me just look it up. I feel like I need to at least touch this equation sheet a couple times a year. So they give it as 6.626 times 10 to the negative 34th joule seconds. And guys, please understand that is not joules per second, it's joule seconds. We're not going to get into why that's the case, other than to say, and Elijah, could you give me our frequency again? 5 what?
5.09 times 10.
Thank you. 5.09 times 10 to the 14th. And I'm going to do it this way. Oh shoot, not that. Once it's in the bottom, it loses its negative. So guys, I'm going to just put that in the denominator, simply to drive home this idea. Seconds up here cancels with seconds down there. Joule seconds is kind of an interesting construct, but we're just going to say it's what the units need to be to end up with joules. So all right, so guys, I get, what do we get, 3 digits? 3.37 times 10 to the negative 19th joules. Is that close?
Yeah.
Okay. So guys, fundamentally, what does that mean? And what it means is if we were to actually start firing photons of yellow light back at Liam, it's not 1, 2, 3, 4 multiples of 1. It would actually be multiples of this number. Which then, guys, takes us back to the bigger idea that if this energy is a multiple of some value, as Michael suggested, that means that there's only certain places where electrons can be, and there are places where electrons can't be, and consequently Bohr surmised that the electrons were organized into orbits. Schrodinger later suggested orbitals, but guys, the science all ties together. You good? Okay. So guys, before we stop recording, What we're going to do today is, we have about 10 minutes left. I'm going to give you your homework assignment. And then, guys, in class third period, we are going to wrap up the lab. Then, guys, what we're going to do on our short day Monday is we are going to take, short day Wednesday, we're going to take these two equations and we are going to work them backwards. Guys, and just a little foreshadowing, what we're actually going to do is we are going to go into lab on Friday. And we are going to collect the light from falling electrons. But what we're going to do, guys, is we are going to measure the wavelength of that light using what are called spectroscopes. Knowing the wavelength of the light allows us to figure out the frequency of the light. Knowing the frequency of the light allows us to figure out the energy of the light. Knowing the energy of the light allows us to figure out how far these electrons are falling. And we're going to figure out electron structures just like Bohr did 100 years ago. Yeah.
Who came up with those equations?
Yeah, so interesting. So that first equation, the E is equal to lambda nu, that was well established because, did I say E? C. No, sorry, my bad. Let me start again. C is equal to lambda nu. That was an established equation because that doesn't just describe light, it describes any wave. So it describes sound. That if we know the wavelength of the sound and if we know how many sound waves are passing a point, we can figure out the speed of sound. So it works with any wave. So that was an established Newtonian equation, big world stuff. But then this idea of getting into frequency associated to energies of light, that was literally, we call this Planck's constant. It was actually, I think it's Planck actually. It was actually Max Planck, who was actually a research associate of Bohr's.
So this lab is like fairly new, like within the years?
I love that you consider that fairly new. Yeah, absolutely. Yeah, this is 20th century stuff. Understanding we're now in the 21st century. So this was 1900 to 1920. Yeah, so less, not 150, 100, 120 maybe. Yeah, go ahead.
So like in the first equation, like C used to be any wavelength, right? Not everything.
Speed.
Yeah.
Yeah, but understand that when we apply it in this context, we're talking about electromagnetics, and as John pointed out, therefore it's constant.
Yeah.
But this could be any wave and any speed.
I just kind of look here with the other equation, like equal density squared, that just has to be light.
Yeah, no. So we do reserve the value C for the speed of light. I know there's confusion with the calorie, but no, C is the speed of light. So when we're talking electromagnetics, it's C is the speed of light. When we're talking about E is equal to mc squared, C is the speed of light. Understand, describing not an electromagnetic process, but when we use C in the context of C is equal to mc squared, we're talking about the conversion of mass to energy. But yes.
So, with this equation, you said like they already knew about this equation with like Newtonian and stuff. Did they still use C for it? Did they use
No. Yeah, no, because it's really the only velocity that's truly constant. You know, I can make my car go faster. We can make sound go faster. You know that sound travels quicker through denser things. So there isn't a definitive speed, if you will, for anything but light.
So what was the like?
Oh, I think it was literally just velocity.
Just doing speed,
Yeah.
right? 'Cause it could be it's
All right, guys, here's your homework.
Oh my God.
I know. All good things must come to an end. Oh, wait, I got to show you the pictures. Ready?
Where's the good thing?
Continuous, quantized. Here's your homework.
You said all good things. This is not a good thing.
Oh,